Hello, everybody. In this video, we will be covering graph theory, which is contest 4 for ACSL Elementary, and also one of the topics for ACSL Junior Contest 4. Okay, so this video will mostly apply to elementary students because the junior graph theory is a little bit different. So, first of all, why do we learn about graph theory in ACSL? Graph theory is really interesting because it can be applied to almost everything in everyday life. So like every network, like your computer network, your Wi-Fi network, are all connected with graphs. If the rooms in your school or in your house are all connected by hallways, right? That's like a graph. Airplanes, right? They have cities that are connected by paths for airplanes to fly. And these things are used, graphs can be used to model all of these things. But what even is a graph? Well, in terms of ACSL, a graph is a collection of vertices and edges. So an edge is a connection between two vertices. Vertices are also called nodes. So a vertice is these little corners. So A, B, C, and D. Well, these corners are called vertices or nodes. And then, yeah, so you draw a graph by marking points for vertices and then drawing segments to connect them. So edges are just these line segments connecting each vertice. There are many different ways to represent the same graph. For example, these two things, they actually represent the same graph. They have the same nodes and the same edges connecting to the same nodes. Right, so a graph with vertices A, B, C, D and edges AB, AC, BC, AD, and BD can be represented by these two graphs below and many more graphs. So these two graphs represent the same thing. They just look a little different. They just look a little different. So these are called undirected graphs. What is an undirected graph? Undirected graphs are graphs that have no arrows on the lines. So for example, the edge BD, the edge from B to D is the same as the edge DB. So the edge from B to D is the same as the edge from D to B. A special type of undirected graph is called a complete graph, where each node has a direct path or a path of one to every other node. And so in all complete graphs, the number of edges is equal to the number of vertices plus the number of diagonals. So this pentagon graph, the graph with 5 nodes, there are 5 vertices and 5 diagonals, which make 10 edges. And you can see that A has a direct path to B and to C and to D and to E. B has a direct path to A, C, D, E, etc., and etc. So they all have a direct path to one another. That's a complete graph. Now, paths. A path is a list of vertices which are connected by edges. So for example, BC is a path of length 1, meaning there's one edge from B to C. BAD is a path of length 2, meaning 2 edges from B to A to D. And then BADC would be a path of length 3 from B to A to D to C. Now, a simple path is just a special type of path where no vertice is repeated. So BC, BAD are simple paths. BAD, C, BA are not simple paths because B is repeated. Now, a connected graph is a graph where each vertex is able to reach every other vertex. Not necessarily directly, but they're just able to reach them. So for example, here, A might not have a direct path to C, but A can reach C through D or through B. In this case, on the case on the right, it is impossible to reach D, so this is a disconnected graph. Now, a cycle is a path with no vertices that are repeated except for the first. So A, B, C, D, A would be a cycle. All right. Vertices must be listed in the order that they are traveled. So if you go from A to B to C to D, you have to list it as A, B, C, D. A, B, C, D, and B, C, DAB are actually the same cycle, because as you can see, they have the same nodes and they go in the same order. So it's the same cycle, it's the same circle. So in an undirected graph, a cycle is always 3 or more vertices. So because this graph is undirected, a cycle cannot be ABA. This is only for this 3 or more vertices rule only applies to undirected graphs. And the only way to find cycles is by counting by hand. Now, our last topic is traversability. So traversability of a graph means whether or not you can use every edge of the graph only once. So the 7 bridges of Königsberg is a famous example. And this little like math riddle is kind of one of the originating points of graph theory. So here's the problem. There are 2 islands and there are the mainland on the north and south. So these 2 islands are connected to each other and the mainland by 7 bridges. Now, your task is to walk through all 7 bridges only once, starting from anywhere. Can you do it? Okay, so you can pause the video and try it if you want, but now I will show you how to do it. So, this is actually a trick question. There is no solution to the 7 bridges of Königsberg. You cannot use each of the bridges only once and pass through all 7 of them. So how do we know if a graph is traversable or not without having to like list out all possible combinations of all different edges? Here's how you do it. So you need to first find the degree for each vertex. So the degree is the number of edges coming into a vertex for each. So yeah, find the degree for each vertex. So the degree for, on this graph on the right, the degree for the vertex C is 5. Degree for A is 3. Degree for D is 3. Degree for B is 3. And then the number of vertices that have an odd degree must be either 2 or 0. So this means that either all of the degrees either have to be even or only 2 can be odd, and those will be the starting and ending points. Yeah. So this is called a Euler path because it was made by Leonhard Euler, one of the, I guess you can say, founding fathers of graph theory. And he's also a big name in geometry. Okay. So yeah. So you can see the 7 bridges of Königsberg are not traversable because all of the degrees are odd. All right. Try these problems. Which one of these networks are traversable? And pause the video to try it out. And I will show you now. So first you find the degree. So 2, 2, 3, 3. You can see that there are 4 odd nodes, right? 1, 2, 3, 4. So this is not traversable because there can only be 2 or 0 odds. This right here is 4. This is 3. This is 3. This is 4. This is 4. So this is traversable because there are 2 odd degrees. This one, you see 3, 1, 1. This one is not traversable because all of them are odd, and 1 is an odd number. Now this one over here, this is 1, 1, 1. And I don't even need to do this I don't even need to go any further because you can see that there are already 3 odd nodes or odd vertices, or odd degrees, I should say. So therefore, this is not traversable. We already know it's not traversable. Now, finally, for this complicated one, right? We just still did the same thing, even though the edges aren't straight. It's the same process. 1, 2, 3, 4, 5. This is actually 5 in the middle. So this is traversable because there are only two odd degrees. Alrighty, that's it for this video. Thank you for watching, and I will see you next time.